The year is 1700. Newton's laws just dropped about a decade ago. Try to imagine what it would like to be a physicist back then. People had already been trying to understand the world around us for millennia, and we'd made some pretty good progress. Many phenomena were even understood well enough to have a precise mathematical description. Like Archimedes gave us the law of the lever, Kepler gave us the three laws of planetary motion, Galileo gave us the parabolic trajectory of an airborne projectile. But why are all these things true? These behaviors don't seem like fundamental laws of the universe, they seem like emergent behavior of microscopic interactions and instantaneous attractions. Presumably, a planet doesn't decide what to do at each moment by planning out its future trajectory. Rather, it just has some particular instantaneous behavior, and the trajectory that behavior generates happens to obey Kepler's laws. And now finally, with Newton's laws, we have a direct description of that instantaneous behavior. For the first time, we have a physical theory that has a decent claim to fundamentality. Answering why are Newton's laws true with "because that's the way it is" actually sounds pretty reasonable. Maybe those are just the rules of the universe. The universe has got to have some rules, right? It might as well be these ones. The job of fundamental physics, then, is to catalog all the different forces and describe how they work. Newton already handled gravity and contact forces, so the next step is to figure out what else is out there. Think about it. Think about everything you've ever experienced. What forces cannot be explained in terms of those two? Two phenomena would probably stand out if you were lucky enough to have witnessed them both back in the 17th century. Magnetism and static electricity. They're both long-range effects, and they're clearly far too powerful to be gravity given the small masses involved. Permanent magnets are easier to do experiments with, but the results you get are harder to parse, so we'll focus on electricity. Now the goal, of course, is a precise mathematical model of the electric force that allows us to make quantitative predictions, but let's not get ahead of ourselves. The first step is just to play around with it and try and get an intuitive understanding of the factors involved. Now remember, this is 1700. You don't have wall outlets or AA batteries or any concentrated source of electricity. What you do have is an assortment of random materials and the ability to move them around with your hands. And fortunately, that's all you need. Rub some wool against some glass and they'll start to attract one another. Rub some more wool against some more glass and the two pieces of wool will repel each other, and so will the two pieces of glass. And it's not mass that matters here, since the mass of the objects is not changing, at least not in any amount you can detect. There's some other property that's causing this attraction and repulsion. And if you want to understand it in detail, you'd better 1. Give it a name, like say electric charge, and 2. Model it with a number. Since it comes in two different flavors that seem to appear in equal amounts, you might try calling one of them positive and one of them negative. In fact, this works out pretty nicely. Let's run through the different cases real quick. When positive meets positive, they repel. When positive meets negative, they attract. When negative meets negative, they repel. And this perfectly lines up with multiplication. Positive times positive is positive, positive times negative is negative, negative times negative is positive. So maybe the force is determined by the product of the charges, with a positive force meaning repulsion and a negative force meaning attraction. After all, the gravitational force is determined by the product of the masses, so it's a natural hypothesis. But a hypothesis means nothing if you don't test it, so let's test it. There's just one problem. How do you test something you don't know how to measure? Balance scales make mass easy to deal with, but a scale is not going to tell you which object has more charge on it. Fortunately, symmetry comes to the rescue. Let's say you have a bunch of identical metal spheres. The reason they should be made of metal is that it's really good at moving charge around. If you touch a big piece of metal to a charged object, it'll instantly dissipate most of the charge by spreading it out onto itself. So if you've got one charged metal ball and one neutral metal ball, and you touch them together, you can safely assume that both of them will end up with half the original charge. If you instead put 3 of them together, each one will be left with a third. Similarly, you can test if a positively charged ball and a negatively charged ball have the same magnitude of charge by touching them together and then seeing if they behave neutrally afterwards. With these tools at your disposal, you can set up a bunch of experiments where you supply these metal balls with various amounts of charge, put them at various distances from each other, and measure the forces between them. For example, you could suspend them both from strings and measure the angles they hang at, which tells you how strong the electric force is compared to the known gravitational force. Assuming you've done it right, the results should be remarkably simple. The force does indeed depend on the product of the electric charges, which is usually denoted with a Q for some reason, and it also decreases with distance in the same way as gravity does, with an r squared in the denominator. The value of this constant of proportionality k depends on the units you choose for charge. You could, if you want, define it to be 1, in other words, define 1 unit of charge so that the force between two objects a meter apart, each with 1 unit of charge, is 1 newton. Historically, that's not what happened, and the standard unit of charge, the coulomb, was defined in a way that makes the numeric value of k about 9 billion. Looking at this formula, electricity is really as similar as possible to gravity given our earlier qualitative assumptions, that it cares about charge instead of mass, and that charge can be both positive and negative. On behalf of students everywhere, I'd like to thank the universe for making sense. Or at least pretending to make sense if you don't look too closely. But don't worry about that for now.